Hello, I hope everyone are doing well and healthy. My name is Henki Susanto. I am presenting our paper, Reducing Latency in Multi-Tenant Data Center via Cautious Congestion Watch. It is a collaboration with Ahmed Abdul Moim and Professor Brahim Bensau. My presentation will begin with introductions, followed by preliminary investigation of the problem that we're trying to solve. Then we explore different design space for our solutions. Then we have a discussion of the evaluation of the proposed solution. Then I will end with the conclusion. So as we all know that we are now living in big data era where there is massive amount of data that is being generated, collected, processed on daily basis. So this data will be used whether for recommendation, machine learning, and many more. So to accelerate the processing speed, this massive amount of data must be processed in parallel. So one of the application that does data parallel processing, MapReduce, application like this oftentimes deploy and run from inside data center. So in some data processing stage, data oftentimes must be transported between machines. So for example, in our MapReduce example, so some machine that function as the mapper, when they complete the task, they have to forward or send the data to another set of machine that perform as a reducer. So the transport protocol that is used in this in data center usually is a DC-TCP or data center TCP. So DC-TCP is a flavor for a TCP that is specifically designed or modified for data center. So let me give a quick overview of a DC-TCP. Here we have a sender, a switch, and receiver, where the sender sends data to receiver through a switch. So let's say inside the switch we have a switch buffer, where the DC-TCP use ECN threshold to measure the potential congestion in the switch buffer. Okay. ECN is an explicit congestion notification that is used by the switch to notify end host about the potential congestion in that switch. So let me begin with the example. We have 4 packets that arrive at the switch buffer. As you can see that the queue length inside the switch buffer has exceeded the ECN threshold. So what the switch does is you can see that there are 2 packets that above the ECN threshold. So these 2 packets will be marked with ECN marking by the switch. Then switch will forward these 4 packets to the receiver. Then receiver will respond or send TCP acknowledgement to the sender, just like any regular TCP. However, since 2 of the packets has been marked with ECN, then 2 of these packet acknowledgement packet will carry ECN echo back to sender to notify about the potential congestion at the switch. So DC-TCP was designed to address an in-cache problem. So in-cache problem is a bloated buffer that is caused by a burst of packet that arrive at the same point and at the same time. So let me give you an example. We have 3 workers or 3 servers that is doing a data parallel processing. So imagine if they send data and all packets arrive at the switch buffer at the same time. Okay, and so as the switch buffer become filled with the packet, so those packets that cannot be stored in the switch buffer will be dropped. And this is quite a common occurrence in data center, especially with the presence of data paralleling processing application like MapReduce. So now we would like to discuss that we did a preliminary investigation to better understand of how well the DC-TCP coping with the in-cache problem. Then from our investigation through a NS2 simulator in dumbbell network topology, so we see is that short-lived flow are sensitive to the choice of the initial sending window size. Okay, and another thing that we see is that since the way the DC-TCP marking is designed, so DC-TCP is aggressive in acquiring the available bandwidth. So it means is that this is TCP favor large flow over the short-lived flow. So example of large flow is the data backup traffic. So we further make a further analysis and delve deeper in the problem to understand what is the root problem of the performance degradation from incas. So from our analysis, we make the two following observations. The first observation is that short-lived flow, which typically could be between consists of 1 or to 5 packets, may not have enough packet to generate 3 duplicate acknowledgement packets to trigger TCP fast retransmission scheme. In another case, the sender may lose the entire window of packets. So for this reason, to detect the packet drop, then sender must rely on TCP retransmission timeout, which typically in Linux settings the RTO is set to 200 milliseconds to 300 milliseconds. Another observation that we make is that incas problem primarily affects short-lived flow. It's just because of many of the today parallel processing application like MapReduce generate many short-lived flows. So then this in summary, that our findings show that short-lived flow in DCTCP still suffer from packet loss due to the use of large initial congestion window that result in incas problem. Okay. Then we ask ourselves, so what is the optimal choice of initial congestion window for DCTCP that mitigate incas problem while minimizing the average completion time of short-lived flow? Okay. So before we go into the solution design, we would like to explore what are the design space, with the hope that it will give us a more holistic view of the problem and better understanding on the complex interaction between network components such as switch, sender, and receiver. So let me begin by explaining our exploration of design space at the sender and receiver. So here we have a sender that send data to a receiver over switch. So based on how DCTCP was designed, there is a wealth of information that are available at the sender end. So for example, number of transmitted packet and congestion window size, RTT, and many more. And on the other end, the receiver has the nature positions to evaluate information carried by packet with ECN marking from the inbound or incoming traffic. So imagine by combining information that gather at both sides, the sender and the receiver, then we will have a richer and more holistic view of the network conditions. So now let's explore the design space at the switch. So we have a case study here. We have 3 workers and trying to send data to an aggregator through a switch. Okay. So at time t, we have worker 1 and worker 2 send packet at the switch, and that which they arrive at the switch buffer at time t. Okay. Afterward, these 4 packets are drained. Then at time t plus 1, packet from worker 3 arrive at the switch buffer. So the lesson here is that is from this simple example is that transmitting packet at different time helps us to mitigate packet drop. So I will invite you to look at the problem differently. So using the same case study where we have 3 workers sending data to aggregator through a switch, but here we have a switch buffer at time t and switch buffer at t plus 1. Let's rotate this switch buffer by 90 degrees. Then we have packet arriving from worker 1 and worker 2 at time t. Then at time t plus 1, we have packet that arrive from worker 3. So this setting actually reminded us of bin packing. It's that in a way that the the switch buffer can be visualized as a bin, and the item here, the packet here, can be visualized as item that need to be packed into the bin. So by visualizing in-cache problem as a bin packing will give us different perspective in understanding in-cache problem. At least give us the starting point to think of how to transmit a bulk of data of short-lived flow, which usually consists on just a few packets. And by doing so, it also allows us to use some of the analysis or insight to solve bin packing problem. In fact, our solution was inspired by next fit algorithm, which is one of the classical solution that is to solve bin packing problem. The way we emulate bin packing is by utilizing ECN that is used in DC TCP. So to solve this problem, we begin by some theoretical work. Our theoretical work can be referred in our paper, but here we would like to highlight some of our result. So the key result from our theoretical result is that, the key insight from our theoretical result is that our results show that the initial congestion window size can be approximated by leveraging information based on number of packets that marked and unmarked by ECN. And given number of packets marked by ECN, the first n transmitted packets should be transmitted in at least 2 batches or 2 rounds. So we, despite of encouraging a positive outcome from our theoretical result, to realize the theory to a practice, what I mean by practice is being able to implement and deploy our solution in the actual data center. So we must consider some of the practical challenges. So for example, we have in-cache problem. In-cache problem is a distributed online problem. However, bin packing is an offline problem. Another challenge that we have to consider is that short-lived flow may be completed before the sender receives ECN echo through the acknowledgement packet. Another word, short-lived flow may only learn about the network congestion after receiving ECN echo, which is too late by then. So in thinking of our solution, we have the following system design requirement. So the solution have to improve the performance of short-lived flow with minimal impact to the large flow. And our solution has to be simple enough for deployment in data center. What it means is that the solution must be able to be independent of the TCP variation, and it does not require modification at the virtual machine network stacks. And of course, this solution have to be able to address some of the challenges, practical challenges that mentioned in the previous slide. So now I would like to present our solution, EdgeWatch. It is a hypervisor-based congestion watching mechanism. What it is that it is an active network probe scheme or mechanism that incorporates insight from our theoretical result to determine the initial congestion window based on the congestion level in the network. Okay. So I'll give you EdgeWatch in the nutshell. The idea is EdgeWatch will inject probe packet during the TCP synchronization stage, which is at the connection startup. Then this probe will be marked with ECN if this probe packet experience congestion along the way before reaching the receiver. Then receiver will set or decide set the receive window or R window according to or based on number of packets that marked with ECN marking. Then pass the information to sender through acknowledgement packet. Then sender will set the initial congestion windows based on information received from the receiver. And the way that we implement it is that it is done at the SIM layer in both sender and receiver. So the implementation is done through the net filters by inserting hooks in the forward processing path. And EdgeWatch is done by modifying the OpenSwitch kernel data path module. What we did is we adjust the flow processing table. So by doing this, EdgeWatch is deployable friendly in production data center. So next, I will show some of our result from experimental result through simulation and testbed experiment. So this is the setup for in our simulation experiments. So we have a factory topology, and it's done through an NS2 simulator, where we have over 100 servers connected to the competitive switches, and we compare our solution with different type of TCP sources, such as TCP drop tail, TCP red, and DCTCP. So this is the result for our simulation experiment. Some of the performance metric that we use is the average flow completion time for short-lived flow, as an average good put for long-lived flow, persistent queue over time, and bottleneck utilization over time. So what this graph tell us is that EdgeWatch improved the performance of short-lived flow by up to 10 times compared to TCP drop tail, TCP red, and DCTCP. But at the same time, it has a minimal impact to the performance of the large flows. So this is the setup for the testbed experiment, and we build and we deploy the EdgeWatch prototype in our mini data center. And in our data center, we have a factory topology mounted at the 4x grid server, and we use edge core competitive switches as our top of rack switch, and our core switch is a PC installed with net FPGA switch. Here is in our similarly to previous experiment, we have average flow completion time and short-lived flow as our metrics, performance metrics, as an average good put long-lived flows as another performance metrics. So as you can see here is that EdgeWatch also improved the performance of short-lived flow by up to 100%. But at the same time, it keeps the minimal impact to the performance of the large flow. So we asked the question, what is it that makes the EdgeWatch perform better than other TCP setups or TCP traffics? So one of the key reasons is that by dispersing packet transmission over time, it creates smaller size of incache. So this allows buffer to observe the incoming packet with fewer packet drop. So what it means is that fewer packet drop allows short flow to achieve faster completion time. Another key insight is that EdgeWatch does stochastically prioritize the available buffer space to short-lived flow. So this is done by the probe packets indirectly reserve buffer space for the short-lived flow. And the last key insight is that the probing mechanisms function as an in-cache early warning system, allowing the long-lived flow or the large flows. They are actively sending data to scale back and release some of the buffer space for the short-lived flow. So I hope that we have been able to convince you that EdgeWatch mitigate in-cache problem in data center, and EdgeWatch also strikes the balance between improving the performance of short-lived flow while imposing minimal impact on the large flow. And at last but not least, EdgeWatch is deployment friendly in production data center. Thank you. I wish all well and healthy and safe. Thank you.